Hi everyone, welcome back to the Flight Engineer YouTube channel, a channel about aviation, technology, and history. I'm your host John, a mechanical engineer with a minor in aerospace engineering, a private pilot in training, and an enthusiast for all things that burn gas or go fast. This video picks up where the introduction of internal combustion engine fundamentals left off. In it, we'll be discussing the basics of engine systems. This will lay the groundwork for the rest of the series, or can be used as a useful reference. To finish out the first video in the series, we'll talk about basic engine systems. For organizational purposes, I've split these into performance systems and durability systems. These categories of systems generally work to balance one another. The performance systems supply the conditions for combustion to take place and thus useful work to be produced. Meanwhile, the durability systems ensure that the energy and forces of combustion do not damage or outright destroy the engine. We'll look at performance systems first. You may remember this diagram from grade school, known as the fire triangle. It represents the three elements needed for combustion to occur. These elements relate nicely to the three performance systems. The intake and exhaust system provides oxygen to the combustion chamber and removes burnt gases. The fuel system provides the source of fuel for combustion, and the ignition system initiates the reaction. The intake system filters ambient air from around the engine and directs it into the cylinders. In many cases, it will also play a role in the fuel system. The exhaust system is designed to remove burnt gases from the cylinder head and direct them away from the vehicle. A basic intake system will consist of a filter and airbox that conditions outside air, a manifold that collects charge air, and runners that connect directly to the cylinder head's intake ports. The exhaust system will consist of headers that connect to the exhaust ports of the cylinder head, and plumbing to collect exhaust gases and direct them away from the engine. Downstream from the engine, components like the catalytic converter and muffler are used to regulate the sound and chemical emissions produced. The intake system, as previously described, is known as natural aspiration. In a naturally aspirated setup, air is inducted into the engine by the movement of the piston and the valves alone, but this is not the only way to provide air to the engine. Modifications can be made to the intake system so that incoming air is compressed mechanically. This is known as forced induction. Delivery of compressed air to the engine cylinder allows more oxygen and thus more fuel to be burned in every cycle. Generally, an engine with such a system will produce more useful work than a similarly sized engine that is naturally aspirated. The simplest way to achieve this is with a mechanical compressor known as a supercharger. The supercharging system centers around the compressor itself. There are two basic types of superchargers. Roots, or screw-style positive displacement units, provide a fixed amount of air per revolution. Meanwhile, dynamic compressors, like the centrifugal supercharger, compress incrementally more air the faster they operate. Regardless of type, all superchargers will need a drive system that uses either a belt, chain, or a system of gears to drive the compressor off the engine's crankshaft. Because the compression of air inherently generates heat, a charge air cooler will sometimes be used between the supercharger and the intake runners. The most complex form of intake and exhaust system utilizes forced induction by the use of a turbocharger. This works very similar to supercharging, except the power to drive the compressor is not sourced from the engine's crankshaft. In this arrangement, a centrifugal supercharger is paired with a turbine that is driven by energy from the engine's exhaust stream. Both the turbine wheel and the compressor wheel are fixed to the same shaft. In this manner, the engine receives the benefits of forced induction while utilizing otherwise wasted energy from the exhaust. Consequently, both performance and efficiency can be increased simultaneously. The turbocharging system consists of the turbo itself, which combines the compressor and turbine in one unit. A wastegate or valve is often included to vent excess exhaust gases upstream of the turbine once the turbocharger's compressor is at maximum speed. Due to the use of hot exhaust gases for power, turbocharging adds even more heat to the intake air than supercharging does. Consequently, charge air coolers are used in almost all turbocharged applications. Moving on, we come to the fuel system, which has a very simple job: deliver fuel to the engine. However, where, when, and in what ratio fuel is delivered can drive significant complexity into the system. In spark ignition engines, fuel must be mixed with air in very specific ratios to allow for complete combustion. The classic way to accomplish this is with a carburetor placed somewhere in the intake system. Inside a carburetor, the throttle valve allows for the operator to meter the flow of air into the engine. This intake air passes through a restriction known as a venturi. This causes airflow to increase in velocity and, by Bernoulli's principle, decrease in pressure. The low pressure creates a suction that pulls fuel through jets so that it can vaporize and mix with the intake stream. This system is self-regulating. As greater amounts of air pass through the same restriction, velocity is driven higher and pressure is driven lower, so more fuel can be sucked through the jets. These jets are finely calibrated so that a given airflow will always receive a given fuel flow, keeping the mixture ratio constant. A basic carbureted fuel system will consist of a tank where fuel is stored and a lift pump with lines to send fuel to the carburetor. The carburetor will include all the components shown below in the diagram, as well as a throttle, allowing the operator to regulate the power setting. Carburetors are simple and dependable devices, but they have their drawbacks. Rapid changes in temperature, altitude, or power setting can result in poor performance of the engine. In addition, starting the engine in hot or cold conditions can also be problematic with a carbureted engine. To address the carburetor's shortcomings, systems have been designed to provide fuel into each engine cylinder, or in this case, each cylinder's intake port. This port fuel injection replaces the carburetor with a throttle assembly that can measure airflow either electronically or mechanically. With the airflow into the engine known, the correct amount of corresponding fuel can be pulsed or injected into each cylinder's intake port. The basic system starts with a fuel pump that provides fuel at low to moderate pressure. A throttle body or fuel servo measures the mass flow rate of intake air and either meters fuel itself or provides an electronic signal to a controller. Fuel flows to the fuel rail, which feeds the individual injectors. These injectors can either be a calibrated orifice, which receives a constant fuel flow, or an electronically controlled solenoid-type valve. While port fuel injection systems are more complex than a carbureted system, it will generally provide greater power, lower fuel consumption, and a more consistent fuel-air ratio to each cylinder. These systems are also much more tolerant of environmental changes or difficult starting conditions. The two previous systems provide a method for fuel to be mixed together with air before entering the engine's cylinder. For compression ignition engines, and some modern spark ignition engines, however, fuel must be injected directly into the cylinder. Sensibly named direct injection, this system provides fuel straight to the cylinder at extremely high pressure. This is most commonly utilized on compression ignition engines, where fuel must be introduced at a precise time into a hot and high pressure environment. In these systems, fuel pushed through tiny nozzles in the injector is forced to atomize or split into microscopic droplets. These small droplets quickly burn on contact with the air in the cylinder. The direct injection system of a compression ignition engine is almost always the most complex part of the engine. Fuel must be carefully filtered before being delivered to the injection pump. While almost all fuel systems utilize a filter, it is most critical in this arrangement. The injection pump uses extremely tight tolerances to create high fuel pressures. Because of this, any particulate not filtered out would quickly damage the pump. The injection pump itself resembles a scaled-down piston engine and is driven through a gear train by the crankshaft. It uses a set of cam-driven plungers and carefully cut ports to force metered amounts of fuel into the high-pressure fuel lines. These heavy-gauge lines run to the injectors themselves, which are carefully manufactured to produce the proper spray pattern and atomization inside the combustion chamber. Note that this injection pump style of compression ignition fuel injection is just the simplest form of the system. Cam-driven and electronically controlled systems are common today, and modern fuel injectors are incredibly complex components that really deserve a discussion of their own. Moving back to spark ignition engines, we'll look at the ignition system itself. Spark ignition engines use a unique two-circuit high-voltage electrical system to generate the spark required for combustion. The primary circuit of this system, operating at the low voltage of the vehicle's battery, is passed through a coil, inducing an electromagnetic field. At specific points in the engine's cycle, this primary circuit is broken. When this happens, the electromagnetic field collapses in the coil. The section of the coil that connects to the high-voltage circuit is excited by this rapid change in electromagnetic field. This creates an intense pulse of high voltage that can be used to initiate combustion. The system is based off the ignition coil, which links the low voltage and high voltage circuits as described. Both the breaker points and the distributor are connected to the engine, and they rotate at the same RPM. Due to this, the breaker points can interrupt the primary circuit, and the distributor can direct the energy in the secondary circuit in time with the engine's operation. The distributor sends those pulses of energy to the correct cylinder spark plug, where the high voltage jumps a gap between electrodes. This arcing provides the ignition source to the combustion event. The traditional ignition system has some drawbacks. If the engine is operating at very high speed or has many cylinders, the ignition coil may not have enough time to generate the voltage needed for a good spark. Additionally, spark timing is mechanically set in these systems and has little ability to change over the engine's operating range. To address this, some engines use multiple ignition coils and do away with the distributor altogether. In some cases, a coil will serve 2 or 4 cylinders, but it is increasingly common for each cylinder to get its own coil. This coil on-cylinder arrangement has the added benefit of reducing the length of the spark plug wires that can be a point of loss for the system. These systems use a sensor that measures crankshaft position and an electronic control to break the low voltage circuit initiating the spark event. From here, the interactions of the primary and secondary circuits and the function of the plugs is similar to the traditional system. With air, fuel, and spark handled, complete and controlled combustion will take place. While this is the intended result, combustion events can damage or destroy an engine surprisingly quickly if heat energy and mechanical forces are not properly managed. This is where the cooling and the lubrication systems come in. The cooling system's job is to remove heat from the combustion chamber, valves, and other components, protecting them from damage. Combustion flame temperatures can range from 1500 to 2500 degrees Celsius, or 2000 to 4000 degrees Fahrenheit. While these extreme temperatures only occur for a short time, they are well beyond the melting temp of the engine's components. The system operates by circulating a liquid coolant, typically a combination of water and ethylene glycol, around the engine components. The coolant absorbs heat energy from the engine's internals and carries it away to a radiator or heat exchanger where the heat can be dissipated to the surroundings. The typical cooling system starts with the cooling jackets running through the cylinder block and cylinder head, where coolant can flow and pick up heat. An engine-driven pump circulates the coolant throughout the system. A thermostatic valve can be used to regulate the amount of coolant sent to the radiator versus how much is recirculated within the engine. This serves to regulate a constant operating temperature. Finally, the radiator allows a path for the coolant to flow where it can reject its heat to ambient air and return to the engine. In some applications, typically marine ones, the radiator is replaced with a heat exchanger. This allows for water glycol coolant to transfer its heat to seawater pulled from outside the vessel. The heat exchanger allows for the two fluids to transfer heat without actually mixing. Liquid cooling systems are extremely efficient at removing heat from an engine, but can become heavy and complex. Some applications can benefit more from an air cooling system. Air cooling can be a lightweight and mechanically simple way to remove excess heat from an engine. In this arrangement, air is flowed around the exterior of engine components. Understandably, any application that utilizes this cooling system must encounter or produce a high volume stream of cooling air or risk overheating the engine. Components of an air-cooled engine will have cooling fins cast into their cylinders and cylinder heads. This increases the amount of surface area over which heat transfer can occur to the air. Large amounts of surface area are required, as air is far less thermally conductive than any liquid coolant. The engine enclosure will typically include ducting or baffles to direct the proper flow of cooling air over the components. Operator-adjusted flaps are often included to regulate airflow when less cooling is required. Finally, many air-cooled engines will include an oil cooling radiator. With the absence of any liquid cooling on these engines, the oil can quickly become a vector for the engine to reject heat. Therefore, the engine's oil must be cooled to maintain its proper operating temperature. It's worth noting that air cooling and liquid cooling can be combined in some cases. This typically manifests as an engine with air cooling fins on the cylinder and water cooling jackets on the cylinder head, where heat generation is most intense. Finally, we come to the lubrication system. This system is arguably the most critical to an engine's continued operation. The oil system is like the heart and circulatory system in the human body. The quickest way to destroy an engine is a stoppage of the oil pump or a blockage of its associated passages. Furthermore, the quality and cleanliness of the oil flowing through those passages is critical to long-term reliability. The primary job of the lubrication system is to supply cool, clean oil at high pressure to the engine's bearings. Any region of the engine that experiences sliding or rotating contact needs high-pressure oil films to prevent metal-to-metal contact. Without this film, even the most advanced materials would quickly break down under heavy operation. The oil also serves to remove soot and contaminants from the engine, as well as carrying away the heat from friction and combustion. Lubricating oil begins its circuit in the oil sump, where oil is stored and where it drains back to after use. Oil is pulled through a filter which removes any contaminants or debris from the fluid. After filtration, an oil pump raises the pressure of the system. This high-pressure oil is forced through galleries in the cylinder block and the crankshaft so that it is delivered to the engine's bearings. At minimum, an engine will have a set of bearings for the crankshaft main journals, the big end of the connecting rods, and the camshaft journals. The basic oil system has remained largely unchanged for decades. Improvements in bearing material and advances in the lubricating oil itself have been critical. However, the basic arrangement of the system is adequate for most applications. That being said, a traditional oil system can be improved. Dry sump oiling removes the gravity-fed reservoir from the bottom of the engine in exchange for scavenge pumps. These pumps collect free oil in the crankcase after it has been used by the bearings. A primary benefit of this system is that oil does not need the consistent force of gravity to return it to the reservoir. It also pulls air and oil away from any rotating components of the engine, reducing the weight and drag on these parts. Finally, the collection of oil in a remote reservoir can reduce aeration in the fluid and lower its temperature. In the typical dry sump system, scavenge pumps pull oil out of the crankcase and deliver it to a remote reservoir. From there, the oil follows the traditional path, being filtered, cooled, and pressurized for delivery back to the engine. This concludes our overview of engine systems and this introductory video as a whole. I hope that this information is useful in your understanding of IC engines. Please leave a comment if there are any questions, or if you would like to see any of these topics elaborated on in their own videos. Like this video if you enjoyed or learned something new, and subscribe to see the next videos in this series. You can also follow me on Instagram, where I post aviation photography, notifications about new videos, and anything else I find interesting. Thank you all so much for watching.